Hello, I'm Professor Von Schmohawk, and welcome to YU. In the previous lecture, we introduced a general method of solving quadratic equations called completing the square. Before the method of completing the square was developed, only very limited types of quadratic equations could be solved. This method eliminated those limitations, allowing the solutions of any quadratic equation to be found. As mathematics progressed, this methodology was eventually reduced to a formula. Given any general form quadratic equation ax squared plus bx plus c equals 0, the values for the constants a, b, and c are entered into the formula that then produces the solutions to the equation. In other words, given the values of a, b, and c, this formula tells us the values of x that will cause the quadratic expression to have a value of 0. In this lecture, we will show how this quadratic formula can be derived from the process of completing the square and show why the quadratic formula is so useful. To derive the quadratic formula, we start with the quadratic equation in general form. The first step is to eliminate the coefficient of x squared by dividing both sides by that coefficient. Next, we change the quadratic expression into a perfect square by changing its constant term, as we saw in the lecture completing the square. In that lecture, we saw that if the value of a quadratic expression's constant term is the square of 1/2 its x coefficient, then that quadratic expression will be a perfect square. As we also saw, the quadratic's constant term can be replaced with this value by first subtracting the constant term from both sides of the equation, and then adding the new constant value to both sides. Since this makes the quadratic expression on the left a perfect square, it can be written as x plus 1/2 the quadratic's x coefficient quantity squared. Then on the right side, instead of squaring the entire fraction b over 2a, we can square all the terms in the fraction separately. The two fractions on the right can then be combined by creating a common denominator multiplying the top and bottom of the fraction c over a by 4a. The denominator 4a times a is 4a squared. And since the two fractions now have a common denominator, a single fraction can be formed by combining their numerators. Now, to eliminate the square on the left side of the equation, we take the square root of both sides of the equation. As we have seen, since the square root of the square of an expression is the same as the absolute value of that expression, the square root of the square can be replaced with the absolute value operation. The absolute value of the left side of the equation can then be eliminated if we add a plus or minus sign in front of the right side. Then on the right side, instead of taking the square root of the entire fraction, we can take the square root of its numerator and denominator separately. And taking the square root of the denominator, 4a squared, we get positive or negative 2a. However, since the entire fraction can already be positive or negative, the plus or minus sign in the denominator is redundant and can therefore be eliminated. We then move b over 2a to the right side by subtracting it from both sides. And since both fractions on the right have a common denominator, a single fraction can be formed by combining their numerators. We now have a formula that gives the values of x that are the solutions to any general form quadratic equation. This famous formula is known as the quadratic formula. Although the quadratic formula solves quadratic equations using the same logic as completing the square, it is more straightforward to use. As an example, in the lecture Completing the Square Part 1, we solved the quadratic equation x squared plus 9x plus 12 equals 0. Using the technique of completing the square, we arrived at the solutions -9 plus or minus the square root of 33 over 2. Let's now solve this same quadratic equation using the quadratic formula. This quadratic equation is in general form, and the constants a, b, and c are 1, 9, and 12. Substituting these values into the quadratic formula, we replace a with 1, b with 9, and c with 12. So the solutions to the quadratic equation are quickly produced. As we saw in Completing the Square Part 1, the graph of this quadratic function crosses the x-axis at the two values of x that are the solutions to the quadratic equation. We have seen that quadratic equations may have two real solutions, a single real solution, or no real solutions. So let's see what happens when we use the quadratic formula to solve a quadratic equation with a single solution. The quadratic function 4x squared plus 20x plus 25 is a perfect square. And like all perfect square quadratic functions, it has a single x-intercept and thus a single 0. Now let's form a quadratic equation by equating this function to 0. Then, using the quadratic formula, we can find the solutions to this equation and thus the zeros of the quadratic function. This quadratic equation is in general form, and its constants a, b, and c are 4, 20, and 25. We now substitute these values into the quadratic formula and simplify. Replacing a with 4, b with 20, and c with 25, we see that the numbers under the square root sign reduce to 0. And so the plus or minus sign adds or subtracts a value of 0, resulting in a single x value instead of two x values. The quadratic formula therefore produces a single solution, -5/2, that corresponds to the single 0 of the quadratic function 4x squared plus 20x plus 25. So far, we have seen that the quadratic formula produces two solutions to a quadratic equation when the corresponding quadratic function has two x-intercepts, and a single solution when the function has a single x-intercept. But what happens when the function has no x-intercepts? To find out, let's apply the quadratic formula to the function x squared plus 6x plus 10. Once again, we equate this function to 0 to form a quadratic equation, and substitute the values for a, b, and c into the quadratic formula. Replacing a with 1, b with 6, and c with 10, we see that the numbers under the radical sign reduce to -4. And since negative numbers have no real square roots, this equation has no real solutions. As we have just seen, the value of the expression under the square root sign in the quadratic formula tells us important information about the quadratic equation we wish to solve. This expression, called the discriminant, tells us the number of real solutions that exist for the quadratic equation. If the discriminant is positive, the quadratic equation has two distinct real solutions. If the discriminant is 0, the quadratic equation has one real solution. And if the discriminant is negative, the quadratic equation has no real solutions. In our first example, with the quadratic equation x squared plus 9x plus 12 equals 0, the discriminant was 9 squared minus 4 times 1 times 12 or 33. Since the discriminant is positive, this quadratic equation has two distinct real solutions, and the corresponding quadratic function has two distinct real zeros. Likewise, in our second example, with the quadratic equation 4x squared plus 20x plus 25 equals 0, the discriminant was 20 squared minus 4 times 4 times 25 which reduces to 0. Therefore, this quadratic equation has one real solution, and the corresponding quadratic function has a single zero. And in our third example, with the quadratic equation x squared plus 6x plus 10 equals 0, the discriminant was 6 squared minus 4 times 1 times 10 or -4. Since the discriminant is negative, this quadratic equation has no real solutions, and the corresponding quadratic function has no real zeros. As we have seen, this is because no real number exists that is the square root of a negative number. However, in the next lecture, we will introduce an extension to the real number system that allows the square root of negative numbers to be represented. This extension is created by a mysterious new set of numbers called imaginary numbers.